All right. This class is being recorded, so I hope that you enjoy it as much as I do. You are being recorded. Your face.
Just that way, right?
There's no video. They're getting what's on the computer screen. This is what they see.
I have a problem with that.
Well, you used to be my best class. No.
Now we are.
No.
You know.
No.
All
right.
Texted me yesterday during 6 hours telling me how bad he failed the quiz.
You did. So, like,
Hey, I didn't take it.
You guys were in the 40s, they were in the 50s, and the other class was in the high 60s. Or the 80s. Thank you. All right. Are we ready? I'm ready. Page 5. I really need you to focus with me today. Because the stuff I go into is pretty complicated. I love it because I don't know, I wasn't a nerd in high school, but somehow I've become one. All right? The first 20 minutes is really physics, and that's what I like. That's what I went to school to be, a physics teacher. I love physics. And chemistry is really close to being physics, so it's good enough. Anyway, we're going to get kind of deep. It'll be all right. Just stick with me.
Was anyone really here?
That I'm blessed with in life is taking stuff that's really complicated and making it even more complicated. Go team, are you ready?
Easy. I got so excited.
Yeah,
I was like,
no.
yeah.
Actually, I was joking. I'm good at making weird stuff that seems hard, not as hard. Okay, here we go. In 1900. Okay, first off, subatomics. No, don't do it, Jimmy. That means we're talking about stuff that's really small. And in this world, like when you get extremely small scale stuff, everything we think we understand and know blows up. Because the world we live in is governed by math. Everything is mathematically governed. But the problem is when you get super small, math changes. And everything that we think we know kind of blows up. You can't treat it the same way. And so what we're talking about is so small that we end up in a world where things are a little bit weird and awesome. Half of today is simply about light. Light is probably one of the coolest things in science. Now, when you take physics, it might bore you out of your mind. No pun intended if anyone got that one. Whatever, it might be. But the science of light, where it comes from, how it travels, all that stuff is so cool. Anyway, here we go. In 1900, Max Planck, or Planck, he was German, but whatever, he introduced the idea of quanta to explain the spectrum of light emitted by certain heated objects. Okay, now, go ahead. What? They absolutely are. Quantum physics just means the study of quanta. And quanta isn't really a thing, it's a measurement. And Zenik, don't make me regret putting you right there. You've asked for months. I finally gave in. All right. You never asked? Yeah, you did. Okay. Moving on.
It's nice that you did it.
You're welcome. Okay. So quantum physics really just means the study of really, really, really small stuff. Okay. Now what we're going to try, what I will try to do is apply some of these things to stuff in your life that might make sense.
God bless you. Each and every one.
Thank you. About time. All right. Now, so when we talk about the light emitted by a certain heated object, think about the following. When you turn your stove on, after a minute or two, what does it look like?
Right.
It's red. It's orange. It's hot, right? We've passed electricity through a metal or ceramic or glass now. They're a little bit different, but we've taken this thing and just heated it up, and now it's emitting light. That doesn't seem weird to you. You're used to that. But back in the day, in 1900, that was very bizarre. Why did things give off certain colors of light at certain temperatures? So Max Planck's going to come along and explain this. 10 seconds, go.
I read somewhere that scientists found out that that certain like not being able to perceive by our eyes, but our hands and head emit light.
Oh, absolutely. We have our own frequency of energy we give off. It's just not in the visible spectrum.
So is that why they have infrared signature?
What?
Or like if they use certain goggles, they can see infrared signature? Or is that just
Yeah, infrared goggles. I give off heat. Heat is infrared energy, and that is there. Now, night vision goggles are not necessarily the same thing if you think they are. Some are, but most are not. Okay, here we go. So Max Planck's idea was that energy is not given off continuously, but in small packets called quanta. And on the test, I made a second set of flashcards, by the way. And then I discovered that app, you can download it to your phone. Study Blue. Hold on. You probably already knew this, but whatever. I'm old. Get over it. Then you can just do your flashcards on your phone. Hold on. And then they'll be there. So compound, and then you say in your mind if you know it, and then you flip it. If you're right, you give yourself a thumbs up. If you're wrong, you give yourself a thumbs down. You just keep on flipping through them. I've added 2 sets now. It's a third of the entire test are matching terms, and they're on there word for word now, exactly how they'll be on the test. It's on my website. What? It's called Study Blue. And it's free. I don't think, you might have to sign up for Study Blue, but it's free also. But I don't think you do, but you might have to. Okay, moving on. All right. So Planck's idea was that energy is not given off continuously, but in small packets called quanta. The whole reason I said that is quanta is a matching term on your test. Don't write down a definition for it yet, but I will tell you quanta and photon, in that section of matching, they're the 2 most missed questions because you get them mixed up. I'm changing the wording so you should never get them mixed up again. So stick with me, but hopefully by the end of the next 5 minutes you're okay. Now, above these notes is a little bit of white space. Will you please draw the following? Stairs and a ramp.
Right here where it's blank. Are you next to Einstein?
You're going to draw a different picture next to Einstein.
I'll do it on top.
Do it above, yes, please.
I don't know how to draw things.
Okay, you don't need to write down the bottom left part, but if you want, you can, but you don't need to. All right, so stick with just this concept I'm trying to give across here. Stairs are what we call quantized. All right? Quantized means there's only certain places that you could be on the stairs. Not even going to try to draw a stick figure. Last hour, it just didn't go well. That's too big, but whatever. This star could only live on that stair, or that stair, or that stair, or that stair, or that stair, right? All right? If I'm a person, can I just hover between 2 stairs?
No.
Worst person ever. I'm getting worse at stick figures.
On what your gravitation.
Okay, well, just stick with me. We can't just be between the stairs. We have to be on one or both, right? All right? So the idea of quantized for energy is it's not like a ramp where you can be anything, any value you want. It's more like a stair where you only have certain allowed energies. So 1, 2, 3, 4, 5. In this example, there would only be 5 available energies that you could be at. And what I mean by energies is if, let me get rid of the star. If you fell from here to there, would it hurt?
Depending on how big the circle.
Probably, okay. But probably. All right, now, if you fell from this one to the ground, usually it doesn't hurt when you fall from the bottom one to the ground, right? And then in the middle, it would be medium. So what we're kind of saying in this example is there's only a few spots, like 1, 2, 3, 4, that you could actually fall from. But on a ramp, how many spots are there that you could fall from? Infinite. You could be right here, right there, anywhere you want, because you are progressively or continuously adding elevation. So here's kind of the idea. This is what we would refer to sort of as classical physics. And I just want you to think of a wheelchair. A wheelchair works in classical physics. We can roll down a ramp. But this is the definition, or sorry, the idea of quantum physics. And a wheelchair would not be able to exist there, right? Or a wheel. Could be a bike, whatever. This is different than what we are used to in our world. Because this happens on such a small scale, we don't really think about it. But it turns out that quantization, or quanta, really does run everything. Okay, stick with me on this little paragraph down here. If all the stairs in this picture were the same size, then the distance between each would be called a quanta. This whole idea of a quanta, all it is a really, really, really small number. All right? And then, like it says, I just said, it would be the small number that all of the values you were at were divisible by. Quanta is the small amount of energy that all energies are divisible by. And it's signified as this weird H. All right, that's called Planck's constant. Now, what I mean by this, all variables would be divisible by, or all values, I can't count, all values would be divisible by it. So what we're saying, let's say this was 5 centimeters tall. Well, how tall would this one be then? Oh my gosh, Pen, work for me, please. This one would be 10, right? This would be 15. And this would be 20. So the idea of quantization is that it can only have certain energies, but each energy is a multiple of one really small number.
And that's why it happens so fast, right? And like so, on such a small scale?
Sure, because this number is times 10 to the negative 34. That's really small, is it not? All right, now, who's lost with me? Wow, only a couple of you?
Everyone else is lying.
I agree. Only 3 of you were listening then.
Yeah.
All right. Hopefully the next thing, you're like, oh, well, why the heck didn't he start with that? Just trust me here. I know what I'm doing. By the way, this isn't the next thing, but this you should know. A photon is made up of quanta. That will help you on your key terms. Go ahead.
I thought also were like the smallest scale, everything was divisible by, so how is the smallest thing made up of
Food?
Quanta's the small thing, photon's the big thing that it's made out of.
Oh, no.
Okay, I'll come back to this idea, but I want to get to right here. Okay, stick with me on this idea here. Money is quantized. All of us are familiar with money.
Oh, yeah.
And money, it has its own quanta, meaning it has a number that everything is divisible by. What in money land, what is our quanta? What do we call it? A penny. No matter what all of us paid for our lunch today, all of it was still divisible by one value, and that was a cent. You with me? All right? But none of us paid like 12.78 cents. There is no value between, unless you're at a gas station, don't even get me started. But there is no value between a cent and 2 cents, right? You're either 1 or you're 2 or you're 3. You okay with that? Every single transaction that is made is a value that is quantized because it can all be divided by a quanta or a penny. Energy is exactly the same as money in that any exchange in energy can be whatever number, but all of those numbers are divisible by one number, and it's called a quanta. Who's with me? Raise your hands if you're with me. No, Connor? You're in the front row now, so you got to pay more attention. All right. This idea revolutionized science at that moment. It really changed everything from this world of classical physics, where anything can be anything, to this world of quanta, where anything can be anything as long as it's a multiple of the same thing. It's a little strange, but that's where we're at. What?
So is there a specific number that is quanta?
Yeah, a quanta is equal to, whoops, wrong button, 6.64 times 10 to the negative 34.
Oh.
That's not even close to being how small it is, right? All right, now, this is going to become important. Remember this idea that there's stairs and falls. Okay, actually, I want to undo until I get back to having it all done. Come on, baby. There we go. All right. So here comes Albert Einstein, which everyone's heard of. Everyone knows his equation. What's his equation? E equals mc squared. That's what he's famous for, but that's not what he won the Nobel Prize for. He won the Nobel Prize for this, and that's his explanation of the photoelectric effect. So, this is a good example. On the SAGE test, you've had these questions your whole SAGE testing career, so 2 years in a row now. They're going to ask about the nature of science. It sounds really weird, but the nature of science is that all science builds on previous ideas. That's all they're looking for. So the multiple choice will be, they disregarded Newton because he was dumb. Or like B would be, they took Newton's ideas and adapted them for new technology. That's what they're looking for. Albert Einstein, 5 years later, he takes someone else's ideas to add and explain something else. That's the nature of science, all right? Remember that. You're going to have 5 questions on them. Science changes as technology evolves, and we add to the ideas of previous scientists. So here comes Albert Einstein, and he's going to win a Nobel Prize for this. Who's ever heard of the photoelectric effect? Oh, like 5 of you. That's a record. All right. Who's ever seen the photoelectric effect? Almost all of you have. I don't know where you saw it, but maybe you've had something like this before. How many of you have left your spoon or your fork and something that you put into the microwave? Raise your hand. Who's ever accidentally put metal in a microwave?
On accident. Arby's sandwich.
Or on purpose? Arby's sandwich.
Yeah,
All right.
simple.
So if you're raising your hands, then you have experienced the photoelectric effect. The photoelectric effect says if I expose metal to high energy light, it will start sparking. Now that's weird. You just have to put bright stuff on it and all of a sudden, boom, sparks come flying out. All right? A microwave, it doesn't use light, but it uses a form of electromagnetic radiation. Anyone know what it's called? A microwave.
What?
Yes. So I'm going to draw this microwave. It's flying in here with a ton of energy. Okay? And it, thank you for the sound effects. The microwave hits your spoon or your fork or whatever. Right now I have oatmeal with my spoon in it. That's the last time I remember doing this, when I was like 12. All right. So here comes this microwave. And metals, they are unique because metals don't own their electrons. Electrons in a metal are free to move wherever they want. That's why electrons conduct electricity. How cool is that? That's why metals bend and don't break. It's why they're shiny. It's why a lot of things. So there's this electron just hanging out on the metal, minding its own business. But then along comes this microwave, and it's going to hit this electron. And when it hits that electron, it gives it energy. And the energy, or the electron will jump. Now listen, it doesn't jump off of your spoon. Okay? It doesn't really move away from your spoon, but the electron will move farther away from the nucleus of the atom that it was closest to. You okay with that? It just moves farther from the nucleus. 1 second. Now, electrons don't like to live far away from the nucleus, so what do you think happens to it? It has to come right back down. But in this world, if it took energy to elevate it, what did it give off when it came back down? It gave back energy. And now we don't see a microwave, we see a spark. Because the energy it released is called light. That says light, because I say it does. Yeah.
Is the reason why the electron jumps is because the energy is positive?
Well, no, not really. Like, it has a positive amount of energy, but a microwave isn't really positive or negative. So kind of yes, but not exactly.
So how do we classify energies then?
Energy?
Yeah.
We just classify it in joules. And it's a positive or negative value depending on the process being endo or exothermic. We'll talk a lot about that, but that's in a different section. All right. So if you think about this real fast, we've taken one form of energy, irradiated a metal, and gotten a different form of energy out. All right. Feel bad. 1, 2, 3, 4, 5 of you gone. 6 gone. This is like my favorite lecture of the year. You guys are wasted. I'm sorry that I'm so boring. All right. Yes, Hannah. No, there is tons of energy that comes off, but the only one I see is it light. Yep. Because the only radiation my body can really sense is visible light. And then, yep, there'd be a ton of stuff here. Okay, now let me apply the photoelectric effect to something that maybe you've done before, and this is, you're going to draw two pictures. You're going to draw this one, and then the next one. So draw this right next to Einstein. So this is his photoelectric effect once again. Microwave is really energetic. It comes flying in, it hits the electron on the spoon, the electron goes up, but then it comes back down. What happened to my down arrow? Didn't I draw a down arrow? No. I never did? All right, it comes back down. As it comes down, it releases energy in the form of light. Sorry, I forgot to tell you. It's a teeny bit more complicated. Well, actually, it's a buttload more complicated. But let's add a teeny bit more to this, is what Einstein really did. When this process happens, it turns out that you can irradiate metals with lots of different values of energy, but electrons only pop off with certain amounts of energies that are always divisible by the same small number. And it turns out that when those come up and fall down, they only emit a specific range of colors. All right? So it was very odd. Like, how come only certain frequencies cause this photoelectric effect, and yada, yada, yada? Well, Einstein takes Planck's idea and says, all right, well, the reason why this frequency of light won't pop something off is because it doesn't match the energy required for that color to be produced. And it was a groundbreaking idea. Now, I don't know that you understand the photoelectric effect perfectly yet, so let's just discuss real quick. This is your other picture. You're going to draw a trampoline. Now, I'm not super good at drawing trampolines. So we're going to say like it has its legs here, right? And we're going to need a net on this one, trust me. Okay? My things come up and point out like this. Okay, and then whoa, my net's not straight.
That's okay.
It's getting worse. It actually looks more like the thing from the first Star Wars. Yeah, it does, huh? All right, it's a trampoline. Now, on this trampoline, you have a person named Logan Larson. And Logan Larson is on this trampoline. And he's just having the time of his life. But of course, it's way more fun if you play games. So he's going to play a game called Crack the Egg.
Oh, bad memories.
And he's going to play it with someone named Haley Sue Norman. Are we all right with that?
Yeah.
Are we okay that he is significantly larger than Haley Norman? Everyone okay with that fact? He's definitely pushing more than 200, and she's definitely not over 100 pounds. Fair enough? Okay. So the way I drew this, we might just be taking and say, oh, we got his whole body. So he's up here having the time of his life with his Dallas Cowboys hat on that I forgot to draw. And she's got her legs crossed. She's holding on to her toes as tight as she can. And then Logan comes in and he does that little trick that we all know how to do, where you just stop and all your momentum goes where? Into the other person. And so where's Haley going to go?
Oh, yeah.
She's flying, right? She's gone. Well, but in reality, what does she have to do? She has to come back down. But listen, if she's like any other human on the planet, she's doing two things right now. She's screaming, and she's kicking. She looks more like a cat in the air than anyone ever, right? Because you don't want to break your neck. So let's think about this. All right, so she's coming back down, and as she comes down, she starts screaming. Are you okay that that's a sound wave?
Yeah.
All right. So now,
She has superpowers.
so think about the following. It's a little bizarre, but didn't we take Logan's kinetic energy and transfer it into sound?
I can see that.
It's a weird process, but it's true, right? His kinetic energy, it was the bouncing. He got kinetic energy and gave it all really to this tiny person. And then as she falls, she releases sound. Who's with me? Okay, that's because we've all played Crack the Egg, right?
Yeah.
Okay, this game is about to step up to a much more dangerous level that I don't recommend anyone does. But stick with me for a second. It might not seem like it, but this is the photoelectric effect. What is Logan in this example?
Microwave.
He's the microwave. She's the electron. What's the sound?
The spark.
It's the spark or the light. What's the metal? It's the trampoline, which really in the long run had nothing to do with anything, did it? Like the metal, it doesn't care that it went in the microwave. So what? It sparked. Well, something happened, but hardly anything really happened. So this is all the same idea. Are you with me? Okay, now, you would never do this because this would be the stupidest game on the planet Earth. But let's pretend that we're like 14-year-old boys and we have no brains. Okay?
That's easy.
And there you go. And we're going to play the stupidest game of crack the egg ever. We're going to add a little bit of intrigue, and we're going to say, all right, I got to just draw this
Let's
over.
light the trampoline on fire.
No, that would probably be
We're
safer.
not that stupid.
Just trust me here. This will all make, well, I don't promise it'll make sense. Oh.
Oh, jump off.
Oh.
Oh,
I don't know that you do get it.
No.
I got to group this ladder together. This is so probably not worth the energy I'm putting in right now. Oh, and then you go that way on me. Okay, so here we go. We're going to play this game now where we're playing Crack the Egg, and we're trying to bounce Haley onto a specific rung of a ladder.
Oh, that's awesome.
That'd be cool, right? You might die, because the odds of landing on a rung are pretty low, right? But whatevs.
Did you do this?
No, I wouldn't do this. Okay, so look. This is where the analogy is really tricky, but just try and stick with me. Logan can bounce her, but she can only land in how many places? 1, 2, 3, maybe 4, right?
So she can land anywhere in the whole vicinity.
Okay, but on the ladder, she can only have certain energies when she lands, right? Which would mean, stick with me, she can only have certain energies when she falls back down. Can you grasp that a little bit?
Yeah.
So listen, no matter what energy Logan puts in, she's going to end up on one of 4 or 5 areas, which means she can only fall 4 or 5 places. And, just to get a little bit, whatever, each time, like if you fall from a high place, the pitch of your scream is going to be higher than if you fall from a lower place, isn't it?
Probably.
Right? Or, stick with me, if this doesn't flow, I'm sorry. Or, this electron, when it jumped up, it could only jump to one of a few areas, which meant it could only do what? It could only fall 1 or 2 or 3 areas, or more specifically, it could only release a couple of different energies of light when that process happened. Now, what does this have to do with Planck? Well, Planck said energy can only have certain values, just like a ladder can only have certain places where the rungs are. And Einstein came along and said, well, all right, Planck, that explains why I get specific colors from specific frequencies, because the electron can only bounce to certain places and only fall from certain places. Now, Yang, you had a comment. Are we over it?
Yeah.
Okay.
Where is
All right. Who thinks they have any idea what I've even talked about today? Raise your hand.
Burley.
Burley?
I got somewhat of an idea.
Who's still
I have a
asleep?
Small grasp.
Okay.
I'm awake.
That kid. Joe, you awake? Barely?
All
right. What? Oh. All right. Look. Oh, that's a bummer. You don't have to understand this perfectly, but you kind of have to have an idea that energy is absolutely quantized. 1 second. That energy determines the colors of light that we see. So when something like this happens, we only will see certain frequencies of light. Go ahead.
So is it always bouncing, or like it bounces, we just can't see the light that it produces? But
Yep. Look, it's going to bounce up into thousands of different rungs, but there's only 4 or 5 falls that actually produce light that my eye can see. If it goes way up here, falls way down here, it's going to give off like ultraviolet or microwave or even, X-rays. So our eyes, as awesome as our eyes are, they are extremely limited on the electromagnetic spectrum. Okay. I don't know. Oh, see, I remember the Dallas hat in that picture. Oh, we better remind you. Bear River's weak, Box Elder is strong. In these falls, when they release light, if you have a small fall, that's a low energy fall, right? And it gives off red. If you have a large fall, large energy, that gives off light that is purple. If you will memorize, Bear River is weak, Box Elder is strong, and you remember that has something to do with their colors, then you'll get most of the core test questions right that are on colors. Okay? Bear River sucks. Just remember that. All right. Einstein, he's a nerd, so he used math. He mathematically determined that light was made up of particles that had discrete energies. Discrete means something that you're not used to it meaning. It means specific. Meaning it can't be just any number on the planet Earth. It's a specific value that is quantized. And all those values are made out of one low value called a quanta. He called these particles photons. Until that time, light was thought of to be only energy carried in the form of waves. All right. A while ago, I showed you a slide that said photons are composed of quanta. The problem is, on the free response, the multiple choice matching section on the test, a photon is a quanta. So how do you distinguish between them? It's weird, because a photon is a quanta, but not all quanta is a photon.
So it's like when you have
So make sure you get those flashcards. And I'm going to change the wording on the test so you don't get them backwards anymore. A quanta says small discrete packets of energy that make up a photon. No one would put photon for that, right?
I would.
That would be silly. You're going to put quanta. Yeah. All right? And then photon, it says, is absorbed or released. What's a small energy that's absorbed or released or something like that. Okay. Now, light is made out of these things that we call photons. The energy of the photon determines the color of the light. The energy of the photon depends on how far this electron fell from where it was to where it ended. The fall determines the color or the energy. All right, now, this was extremely groundbreaking because until this moment, light was just considered to travel and be like a wave. All right, well, that wasn't supposed to happen. It was called an electromagnetic wave, and light is an electromagnetic wave. So light is a wave, but it also behaves like a particle, which can't exist. Like, that just does not make sense. We can't bounce and reflect and refract all at the same time. Light can. So, for instance, you can pick up a radio station from Logan, right? Can you see the radio tower? No. That's because the radio wave refracts. It hits the mountain, and it clears the mountaintops. So here's the mountaintops. Here's our radio wave over in Logan. It hits here, but it's fine. And here I am in my car listening to Kicks 96, because I'm a redneck, whatever. That looks more like a baby stroller. But I can pick this up, right? But if I shot a laser from right here over this mountain, would it come shoot my house?
Yeah.
No, because a laser behaves like a point particle. It travels directly from A to B, right? Whereas a wave spreads out. Well, light does both. Figure that one out.
Oh.
It behaves point-like and wave-like at the same time.
Yeah, that's
One of the coolest things you can ever do, take an empty aluminum can, take one of those old school flashes from your camera that you can push the button on the back. Does anyone have one of those at home?
Oh,
Get it. You have to hang the pop can so nothing's touching it. Put the thing right next to it, the flash, and hit that button and listen. And the light will make the can ping.
What?
You're lying.
I'm not lying.
Wow.
You should do this in here.
I should, but
Isn't that why, like,
the
the
photography room's so far away right
you
now.
know the old cameras that had like the big the domes
Yeah?
that reflect the flash? Is that why they would go?
No.
You take a picture now.
Because they
Oh,
actually
that's
were
from the
burning
powder they use,
phosphorus.
yeah.
Right? So light travels and hits something and it makes a sound. That's weird. That's a property of something that is a point particle, meaning it travels straight. It's a photon. But at the same time, light bends. Like it's all messed up.
Is that duality?
Yep,
Is light,
that's exactly what we're talking about. The dual nature of light. What?
light goes in that.
Originally, yeah, but now they think that the electron has very similar properties, which would make sense because light and electrons are super tied together. Okay, let's blow through this. Robert Millikan in 1909 calculated the charge on the electron in his oil drop experiment. Okay, I'm going to go really fast through this. The electrons were transferred from the atomizer to the oil droplets. The negative charged particles fell through a vacuum under the influence of gravity. I will draw this picture and explain what I've done. So we had oil drops, negatively, and gravity. I haven't heard that all day. I've almost missed it. Millikan adjusted the voltage on the plates to offset the pull of gravity. He found that each droplet had a different charge, but all the charges were a multiple of one small charge. Okay. What do we call something that can have any value it wants, but is divisible by the same number? It's quantized. Okay? So even the charge of the electron is a value that is quantized. All right. Next, he assumed that small charge to be the charge of one electron. What time do we get out of here, Miser? 52. Okay, I got plenty of time. Here's this picture. It looks a little bit weird, but stick with me. He essentially had the following. He had a little thing like a hairspray bottle, like the aerosol ones, the cans. And he sprayed stuff in here that was really, really, really fine. It was called an atomizer. It made oil droplets that were super small. These oil droplets would fall. And then he had an X-ray machine that he would hit these with. That's the worst color ever with white background. He would hit these oil droplets and cause them to become negatively charged. The oil droplet continued to fall, but now it had a negative charge. Millikan had a droplet at the bottom of this machine, not a droplet, a plate, that he would cause to be negatively charged also. What do two negative charges do to each other? They repel. So what he would do is he would adjust this plate until he could get one of these to stop falling. He would look right through here with his eye. This is an eyeball in physics. All right? He would look through there and watch this thing stop. Then he would write down the number that he had to make that to get the thing to stop falling. He did this over and over and over and found thousands of numbers. It was actually his TA. His professors don't do any work. They're TAs. Every one of those numbers was different, but what did they have in common? They were all divisible by the same number. And he said, hey, that has to be the charge of the electron. I feel like you think we're done.
Wait, what was the number?
I guess we'll be done. I don't remember what a coulomb is. It's 1.8 something. 1.8 something. I can't remember.